can get to any number you like by counting, right? So there's two things you can do. Firstly, from nothing you can start counting. And secondly, if you've counted to a number, you can count to one more. I counted up to the 1 billion in the back of my car when I was a kid. Now I think I went up to like 1,000,010, then went up to 1 billion or something. But I thought I could count up to 1 billion by following that procedure. It was like 3.5, not very good at stuff. So if I follow those two rules, I can get to any number, right? I just wrote those down. You choose 0, and you just keep on adding one more. That will get us to every single arithmetic number. Just a normal arithmetic. Everyone agree with that? I do. This isn't a trick. Okay. So if we have rules that let you do this, we have one rule that says it works for 0, and one rule that says if it works for any number, it works for the next number. That means we've kind of shown that it's true for any number in exactly the same way that if we counted. So let's say, we'll write this word out properly. It works for 0. Okay, that's not formal notation. I can't write it. Keep on coming as like logicians. It works for n, so it works for n plus 1. So if I can prove those two statements, it works for 0, if it works for any number, it will work for the next one. Therefore, it works for all numbers. By numbers, I guess I mean positive, whole, whatever numbers. Because if you start with 0, you can keep on just doing the next number till you get to that number. So when I prove something for 17, I say, well, I can prove it for 0. And if I can prove it for 0, I can prove it for 1. And if I can prove it for 1, I can prove it for 2. And if I can prove it for 2, I can prove it for 3. If I prove it for 3, I can prove it for 4. And so on until I get to 17. So it works for 0, and I can keep doing the next steps. So I can prove it for 17. But I don't need to have 17 or 18 proof steps. I have these two steps here, and it gives me an infinite number of results all at once. Because that's how numbers are made up. So that's induction. Some of you will have come across mathematical induction in high school or in mathematics. It's just that idea, and it's because of this plus one-edness or succession. Okay, so let's look at it in terms of natural deduction. If anyone wants to talk about this, this is fine. This is a core concept to get sorted before we move forward. But I'm just going to assume for the blank faces, people are quietly confused. Okay, shouldn't have got rid of the projector because I want that projector on again. I have no planning here. Here is a natural deduction rule. It's one of the ones on your rule sheet. It's the last rule on your rule sheet you probably haven't used yet. If there's other rules on your rule sheet you haven't used, you should have used them. This says, if I can prove some formula A, where x is 0, so if I can prove it for 0, good, and if I assume it works for n, and from that I can prove it for n plus 1, then for all x A. So if we can do these two steps, this is another form of universal introduction. So now we have two forms of universal introduction. One is the normal universal introduction. I'll choose an arbitrary number. The second one is it works for 0, and I can keep on looping around, working for the next and the next and the next one, so I can do it for all of them, so it's done. So that's our rule. It always takes this form here. We still need to prove that if it works for n, it works for n plus 1. We still need to prove it for 0. Both of those will be little proofs, often involving Q, the Robinson's arithmetic. But that's the sort of pattern of reasoning. So let's just give you a very small one to start. It's something that we've wanted to do, well, for the last week. I've wanted to do it for several years. Probably you wanted to do it for the last week. I'm going to leave that up on the board, and I'll just do a small example here, and then we'll get rid of that once people are more comfortable with it. We know that x plus 0 equals x, right? So we need x. We proved that last week. What about 0 plus x? So 0 plus x equals x. Now we don't know if that's true. We know that a plus 0 equals a, that's just q3. But we don't know what 0 plus a is. Because if you keep on taking bits out of a and putting it in front, and we don't know how many times we're going to do that. So we don't know what 0 plus a is. Under Q, under Robinson's arithmetic, we can't actually prove this. But we will prove this using Robinson's arithmetic plus this new induction rule. Okay, so we've got a quantifier, a universal quantifier. We could do universal introduction. Don't write this down, or at least get ready to cross it out. But that's not going to get us very far, because we're not going to break this thing down. So the other thing we can do is this new second form of universal introduction, which is an induction, universal introduction, because we end up with a universe we didn't have it before. Okay, so it always has two parts to it. First part, number 1, number 3, 4, number 2. We will assume this works for a particular number n. 0 plus n equals n. We're going to assume that holds. And we're going to try to prove 0 plus s of n equals s of n. If it works for any number, it will work for the next number. The second thing, or the first thing I guess we're going to try to prove, is it works for 0. So now we, instead of proving 1 will follow from 2, and the reasoning block 3 to 4. So if it works for these two rules, it will work for everything. I'll just put that up for you to look at. And that's the end of induction. Well, that's the end of the entire class in some sense. The rest is just practice. But you can have a go at proving 4 from 3, and you can have a go at proving just 2. I'll give you a minute or so to do that, and then I'll sort of fill it in. I just wrote down n rather than a because I like to use n's to remind myself it's a number. Actually, the general habit, I use the n when I do induction, and a and b when I use the other universal introduction. I just find it helps me keep track of what's happening. That's just a mental thing that I find useful. Because you'll later on have like 3 quantifiers, one of which is induction and 2 of which are the other ones, and you get confused. If you use n for that, and a and b for the others, because you're treating this thing like a number, the other thing you're just treating like objects. It's a mental trick that I find useful. Even I think of all sorts of things that I find useful. Okay, I'll give this a go myself. I'm going to start with line 2, that looks fairly easy. Okay, it's done. Anything plus 0 is that anything. So x plus 0 is x, we know that, that's just q3, so one line. Normally it's a bit more of a complicated proof for this, but with this step we're doing isospecially here. Okay, this is an identity, so that identity is going to come from a block of reasoning. Identity introduction from line 5 to line 5, 0 plus Sn. 0 plus Sn, we've got an S on this side, so that means S of 0 plus N. Assumptions, that equals block. This is by Q4. Now, 0 plus N, we know by line 3 is just N. You usually, do not always, get to use this assumption. So I'm going to use line 3 to replace the 0 plus N with N. And I'm done. Put that further up so you guys can stare and admire the fact we can now add anything to 0 and end up with that anything. This brand new result of powerful mathematics that we didn't have before. The reason why we're doing that is we kind of have to do